And finally, in this lesson, we look at image formation by mirrors, because mirrors can also be used to form images. And you're all familiar with this if you have a bathroom mirror. Clearly, you look at your own reflection in the bathroom mirror, your own image, in order to get ready in the morning. If you have a car, you have a rear view mirror and side view mirrors. These allow you to see the images of what's behind you and to the sides of you. So mirrors are very useful in terms of creating these images. Now, we're going to be looking at spherical mirrors in particular. So if you imagine a sphere, imagine you have an actual ball, and you put silvered material on either the inside surface of the ball or the outside surface of the ball, then that surface can act as a mirror. So here we have the center of the sphere of radius r. So the entire sphere, of course, has the same radius. If we take, the dotted line shows where the sphere would be. If we take some section of the sphere, let's imagine that this is mirrored. So this has in the interior of this part of the sphere is mirrored. If we send parallel beams of light towards the inside portion of the mirror, we find that they are reflected through a focal point. They all converge at a focal point. And that focal point is halfway between the center of the mirror and the edge of the mirror. Or in other words, the focal length of this spherical mirror is equal to the radius of the sphere it would have come from divided by 2. This is the rate called the radius of curvature. Half of the radius of curvature is the focal length for a spherical mirror. Now there are two types of spherical mirrors. You can either put the mirrored surface on the inside of the sphere, or you can put the mirrored surface on the outside of the sphere. If you place the mirrored surface on the inside of a sphere, then you have the mirrored surface on the concave portion of the sphere. This becomes a converging mirror. Like I have drawn here, parallel beams of light are focused down to a focal point. Just like a converging lens takes parallel beams of light and focuses them down to a focal point. So you have parallel beams all go through the focal point, which is some distance from the intersection between the optical axis and the mirror. That's our focal length. Conversely, we can have the outside of the sphere mirrored, and what happens in that case is parallel beams of light shown at this surface diverge. They spread out. They don't come together to a point. They appear to all diverge from this same point on the other side of the mirror, the focal point. So this is a diverging mirror or a convex mirror. And like with lenses, we had converging lenses, we gave them a positive focal length. Converging mirrors also have a positive focal length. Diverging lenses and diverging mirrors have a negative focal length. So if I say I have a mirror with a focal length of negative 10 centimeters, it's a diverging mirror. Or if I say I have a diverging mirror with a focal length of 20 centimeters, I know the focal length is really negative 20 centimeters because it's a diverging mirror. Now, besides that distinction between mirrors and lenses, the equation to figure out the object distance and the image distance is actually the same. So if we know what the object distance is from the mirror, and we can figure out what the image distance is from the mirror by looking at the focal length of the mirror. And some mirrors, again, making sure that converging mirrors have a positive focal length, diverging mirrors have a negative focal length. We can determine what the image distance is, and if that image distance is negative, it is a virtual image. If that image distance is positive, it's a real image. Now, distinction here, for mirrors, unlike with lenses, the side at which a real and a virtual image appear flip. For mirrors, real images are on the same side as the object. Virtual images are on the opposite side of the mirror as the object. And the way to think about that is think about your bathroom mirror, right? The image you see of yourself is a virtual image. The rays of light really don't go behind the mirror. Those rays of light bounce off the surface of the mirror. They stay on the bathroom side of the mirror, not behind the wall. It's a virtual image. It's on the other side of the mirror. So mirrors and lenses, spherical mirrors and thin lenses have the same relationship. Converging mirrors and converging lenses both have positive focal lengths. Diverging mirrors and diverging lenses both have negative focal lengths. The sign convention for real and virtual images are the same. The sign convention for magnification is the same. The only distinction is for mirrors, real images occur on the same side as the object. For lenses, it's the opposite side. And virtual images for mirrors occur on the opposite side of the mirror, and for lenses, they occur on the same side. So there's a distinction there between lenses and mirrors. Otherwise, the convention and the equations for mirrors and lenses are very similar. So look at the examples that your book gives you, and look through the examples that I work out in my homework videos to get an understanding of how to solve problems with thin lenses and with spherical mirrors.